Hello everyone, once again I welcome you all to MSB lecture series on transfer chemistry. We have been discussing the classification of ligands by donor atoms. So far we have completed most of the ligand systems and we are discussing about oxygen donor ligands. We have numerous examples of oxygen donor ligands. Let us consider a few prominent ones. For example, if you take alcohols, aryl alcohols or alkyl alcohols, they can be readily deprotonated and reacted with transition metals to form the corresponding alkoxides or aryl oxides. Let me consider a general reaction. So, something like that, initially this happens and later H plus can come out and it can form something like this. For example, if we consider titanium tetrachloride and that is treated with 4 equivalents of ethyl alcohol in presence of a base such as triethylamine, it can give tetraethoxy titanium . Of course, here 4 triethyl ammonium chloride are formed, and the examples of this type of compounds are also known. Let us say we form a phenoxy compound like this, and they can also coordinate to a hard metal such as lithium, something like this. For example, if we are using lithium phenoxide and make this compound, and the lithium can also get coordinated to this oxygen lone pairs, and then the coordination can be saturated with 2 more THF ligands. Another interesting complex is with uranium. So, these are few examples of mixed ligand complexes, and another important class of ligands we come across are crown ethers. For example, stable complexes are formed by multidentate ligands. The advantage of multidentate ligands are they can very nicely encapsulate a metal ion and have very extra stability. In that context, these two ligands are very important. One is crown ethers and other one is cryptands, and these two ligand systems are essentially used to stabilize cations when we have anionic transition metal complexes. Cations such as alkaline earth metals or alkali metals can be very nicely stabilized, so that compound is stable, and that can also be crystallized very easily to understand the bonding concept, bonding parameters. For example, lithium can bind to ammonia very similar to any transition metal, and we have cationic complex here, and nevertheless if lithium is a counter cation, it is advisable to have some of these crown ethers to stabilize this cation rather than going for monodentate ligands, as they are susceptible for further reaction. So, this is called 18 crown 6, and it is very simple. We have 18 atoms in the ring and 6 oxygen atoms are there. So, that is the reason it is called 18 crown 6. If you start counting from say here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So, 18 atoms are there in the ring, and then we have 6 oxygen atoms are there, and usually it looks like a crown. As a result, it is named as 18 crown 6. and in this case what happens, we have 2 oxygen atoms in between these nitrogen atoms, it is called cryptand 2 and a typical reaction, you take a cation and just put into cryptand, it can form. Okay. Even if you have some other ligands, hard ligands in the coordination sphere of this cation, the moment you put it, because of encapsulation, entropically driven reaction happens, and then these macrocyclic ligands encapsulate the metal to form a stable compound. Stability of these complexes increases if the size of M plus matches the cavity of the crown ether or cryptand we have chosen. So, from this point of view, one has to be extremely careful in knowing the size of the metal and also the size of this cavity. So, that if the cavity matches well with the size of the cation, then this is very difficult to dislodge the metal center, as a result this is more stable. For example, I have shown you, in case if we have to stabilize lithium ion, then the ideal size is 12 crown 4, and if you want to stabilize a sodium cation, the ideal size is 15 crown 5. Similarly, for potassium we need 18 crown 6, or in case of rubidium we need 21 crown 7, and in case of cesium we need slightly larger one, 24 crown 8, and this is how it can encapsulate a cation, one can see here. And now the shape of this crown ether almost looks like a crown, and hence the name crown here. And cryptand can encapsulate from 3 different positions like this. As a result, what happens, it is even more stable compared to the crown ether bound cations, and hence in this also used in case of alkali metals, and preferably and also with alkaline earth metals. They are called cryptands, where we have oxygen as well as nitrogen donor atoms. In case of crown ether, it is homoleptic, it has only oxygen donor atoms, but one can have alkyl groups and aryl groups combined. Okay, now let me give the preparation of crown ethers. Let us consider this catechol. And treat this one with chloroether. In presence of a base such as sodium hydroxide in butanol, and then we need H plus. So, it forms so this is dibenzo 18 crown ether 6. Of course, the name given is correct or incorrect, you can always check that one. So, this is the typical method of preparation of crown ethers. Another important ligand among oxygen donors having cage type structure is called calixarenes. A typical calixarene I shall show you here. Usually tertiary butyl groups are taken here, and because of bulky groups on para position, what happens, it is something like this, it looks like this, and lower rim and upper rim we call. In the lower rim what we have is OH groups are there, and upper rim we have, if it is t-butyl group, something like this we have. Because of if it is t-butyl group, what happens, it enlarges something like this. As a result, it will be having this kind of shape here, and this can also encapsulate, and very versatile chemistry is known with this class of ligands. And resorcin arene is also another class of ligands, okay, where we have 2 hydroxyl groups will be there for further binding. So, with this let me stop discussion on oxygen donor ligands and move on to another very important class of ligands, that is called phosphines. You may be surprised to know that phosphines were known for almost 150 years back, and the first phosphine complex of platinum, that bis triethyl phosphine dichloroplatinum, both cis and trans, were reported in 1870. That means we have a history of 150 years for phosphine chemistry or phosphine complexes, and how this was made. This phosphine was made initially can be seen from this one. Ethyl magnesium chloride was treated with triphenyl phosphide to form triethyl phosphine through the elimination of this one. And of course, during the same time, the first cyclodiphosphosane like this, having this 4-membered ring having alternate, it is a saturated 4-membered ring having alternate phosphorus and nitrogen atoms with phosphorus in trivalent state. Since phosphorus is in trivalent state, it has a pair of electrons, so one can use this as a ligand. The first compound was prepared in 1857, and however, the structure of this complex, this ligand itself was solved only in 1970s. And you can see important review articles. I myself wrote 3 review articles on this one, and we have published more than 50 papers on coordination chemistry and applications. We have carried out extensively coordination chemistry of cyclodiphosphosanes and very interesting ligand system. Some very unusual compounds were made, especially with copper. The interesting thing about group 15 we call nictogens is we saw the versatility of nitrogen as a ligand or a donor atom in coordination chemistry. In fact, when we look into the coordination chemistry that is performed in aqueous medium, nitrogen donor ligands are second to none. In contrast, when we move to the next congener, phosphorus, in organometallic chemistry and as well as in homogeneous catalysis and also in coordination chemistry, phosphines as neutral ligands with back bonding capability are second to none. Look at one below, has very contrasting and complementing property compared to nitrogen, but on the other hand we have numerous phosphorus nitrogen compounds in main group chemistry. And main group chemistry, one of the important class of compounds are phosphosines and phosphosanes having phosphorus to nitrogen single bond and phosphorus nitrogen double bond. Excellent ligand system complementing each other but having contrasting properties. Let us try to understand more chemistry of phosphines as ligands. When we talk about phosphorus donor ligands, the simplest one is a phosphine, very similar to ammonia, and then if you keep on substituting hydrogens with R group, organic groups, alkyl or aryl groups, then you can have primary phosphine, secondary phosphine and tertiary phosphine. Tertiary phosphines are like PR3, and also one can have alkoxy or aryloxy groups on phosphorus. So, when we have 2 groups, we have all or alkoxy or aryloxy, then they are called phosphides. For example, this one, if it is OME, trimethyl phosphide, or one can also call as trimethoxyphosphine. Then of course PF3, PCl3, PBr3 also one can use as ligand, and then we can have a mixed alkoxy or aryloxy group along with this one. This is called phosphonite, and if you have one OR group, it is called phosphinite, and also we can have NR2 groups. So, or we can have all different groups on phosphorus, they are called tertiary phosphines. And apart from this monodentate ligands, we also have numerous examples of bis, tris, tetra and polyphosphines, and also phosphines with heterodonor atoms such as nitrogen are very common, and also we have numerous examples of phosphorus existing coexisting with other donor atoms such as oxygen, sulfur and selenium. Let us try to compare similar ligands which have donor and acceptor properties as phosphines or carbon monoxide, and we had spent enough time discussing the binding properties and similarities between carbon monoxide and phosphines. And similarly, you can see Fischer carbenes if you look into it. Again, you can always make the comparison of sigma donor ability and pi acceptor abilities and heterocyclic carbene, and in case of the phosphines it is sigma star, in case of carbon monoxide or carbenes of these two type it is pi star or back acceptor orbitals. So, that means sigma donation and back bonding is there. The only difference is carbon monoxide, what would happen is of course sigma donor and pi acceptor, but you cannot meddle with the nature of carbon monoxide. In order to call this as a carbon monoxide, there should be carbon and oxygen, but in contrast phosphine, we have an opportunity to perform a variety of substitutions on phosphorus to have different groups that can control the metal activities through both kinetic and electronic ways. For example, phosphine, if we consider more electron withdrawing groups on phosphorus, so that can be poor sigma donor but very good pi acceptor. On the other hand, if we have more electron donating groups on phosphorus, that become very good sigma donor but poor pi acceptor. But having a combination of electron releasing groups and electron acceptor groups, one can match the ability of carbon monoxide or sometimes even supersede the ability in back bonding. For example, if you take PF3 or we have like fluorine substituted organic moieties, they can even be better pi acceptor compared to carbon monoxide. In that context, what happens, there is a flexibility in altering the ligating properties of phosphines that normally we do not see in case of carbon monoxide. This is where we have advantage over carbon monoxide in its utility in organometallic chemistry as homogeneous catalysts for a variety of organic transformations. When we come to Fischer carbene and N heterocyclic carbene, no doubt they are also good sigma donors and pi acceptors, but as I already mentioned in one of my previous lecture, that they also have some lone pairs available for back donation to pi star of carbon. As a result, what happens, it is either in this in carbene or in this N heterocyclic carbene, we have nitrogen lone pair, here oxygen lone pair. As a result, what happens, they have less inclination to take electrons from metal through back donation. As a result, what happens, they are relatively poor pi acceptors compared to phosphines. So, this is where the phosphines top among best sigma donor and pi acceptor ligands, and hence their utility is enormous in homogeneous catalysis. Let us look into the binding again. As I mentioned, phosphorus in trivalent state has a pair of electrons, so that can go to suitable metal orbital to establish metal to ligand bond, that is metal to phosphorus bond. So, preferably it can go to dz square or dx minus y square based on the type of geometry adopted by these metal complexes. Now, you can see here this is about back donation sigma star. Sigma star can interact with say dyz. In that case, what happens, the back donation happens. So, here pi acceptor ability can be readily monitored by having different substituents on phosphorus. For example, if you put more electron withdrawing group like we have PF3 or POR3 or PNR2 thrice or PME3. So, the relative energy of sigma star I have shown. So, the question is, if we say this is a better pi acceptor than PC, how it is. So, you can see, let us say here the energy of T2G orbitals are there, or metal donor orbitals are there, or metal pi donor orbitals are there, and here the relative energies are there. That means by adding more electron withdrawing groups, we are pulling down the sigma star orbitals to be on par with metal pi donor orbitals. So, that means on the other hand, if you put more electron donating groups, the energy of this one is elevated. As a result, what happens, they become good sigma donors but very poor pi acceptors. So, this is where phosphines have remarkable ability to adjust their donor and acceptor properties, and hence they are very important among all ligands in organometallic chemistry and also in homogeneous catalysis. Once again I have shown here MO diagrams for metal carbonyl complexes and metal phosphine complexes, very similar. This represent back donation, that means sigma star is interacting, sigma star acts as a now atomic orbital, and then metal T2G, one of the T2G acts as a atomic orbital, they combine together to generate bonding and anti-bonding orbitals, then electrons are placed here. So, why I am elaborating this one is some students were asking question, although electrons are going for sigma star, why we call it as pi bonding. The symmetry of that one is pi bonding, as a result we call it, and also the electrons are not going directly to the sigma star here, one should remember that one. Even that is true in case of even carbon monoxide or in heterocyclic carbenes. They essentially again combine performing as atomic orbitals with metal atomic orbitals to generate a set of bonding and anti-bonding, and then they stay here. So, this is called back bonding here, and then the pi symmetry is there, although it goes to sigma star, we still call it as pi back bonding for the same reason. Another important, that means we know the electronic effect. Once again I repeat, so electron withdrawing groups on phosphorus makes it poor sigma donor but strong pi acceptor. On the other hand, electron donating groups on phosphorus makes it very good sigma donor but poor pi acceptor. By knowing these two extreme cases, we can have desired groups on that one to have moderate sigma donor and pi acceptor abilities. Then how about steric attributes? What would happen if you have bulky groups on phosphorus atom? Yes, that is another important thing. This one was shown by Tolman. Okay, Tolman showed in his cone angle that when a typical phosphine binds to a metal having a metal to phosphorus distance of 228 picometer, it generates a conical surface like this. Let us assume this is a triphenyl phosphine. You can see here pyramidal structure is there, and this is the lone pair. Now, this lone pair goes to the metal, and this distance is about 2.28 angstrom unit. This is the average distance I am talking about. Now, let us imagine a conical surface, and I put it here, and when I start rotating, that means this cone angle is nothing but the angle subtended at metal with a metal to phosphorus distance of 228 picometer that encloses van der Waals surfaces of all ligand substituents over all rotational orientations. I repeat again, this is the angle subtended at a metal to phosphorus distance of 228 picometer that encloses van der Waals surfaces of all ligand substituents over all rotational orientations. For example, now if I can rotate freely without touching this conical surface, okay, this is called cone angle, okay, for this particular phosphine. Then if I take a say bulky phosphine, let us take a trimethyl phosphine. If you take trimethyl phosphine, so in order to have free rotation of methyl groups on it, I should expand it. That means when you have bulky groups, cone angle increases. Then find how to correlate this one with its reactivity and its utility in catalysis and other reaction. Let us discuss that one in my next lecture. So, you can see here I repeat again how to define cone angle. Solid angle theta can be defined as a conical surface that is encloses the van der Waals surfaces of all ligand substituents over all rotational orientations. This is called cone angle, and here if you see I have listed some cone angle values here. For example, PH3, okay, very small groups, the angle is 87 degree, and then if you go for trifluorophosphine, okay, trifluorophosphine we have fluorine with F minus have, so with one bond we have 3 pairs of electrons are there in each phosphorus, each fluorine. As a result, what happens, the cone angle increases, and then we have trimethoxy or trimethyl phosphite 107, trimethyl we have 118, dimethyl phenyl phosphine 122, triethyl phosphine 132, triphenyl phosphine 145, and if we put cyclohexyl group it goes to 170, and when you have 3 tertiary butyl groups it is 182, and if you have 3 mesotyl groups we have a maximum, I mean it is almost 212 cone angle. So, that means how these cone angles would define the coordination geometry and coordination number of a metal complex, and how we can use this one in homogeneous catalysis. We shall discuss in my next lecture. Until then, have an excellent time reading phosphorus chemistry.